यहाँ पर आपको एजुकेशन, एक्सप्लेनेशन, टॉप 10 क्वेश्चंस, इंपॉर्टेंट क्वेश्चंस और एग्जाम्स के मुताबिक न्यू अपडेट्स मिलती रहेंगी।
My dear students, welcome back to our channel. In this video, I will be explaining the MBA third semester subject DBMS Database Management System as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 4 first important short question is Transaction Processing DBMS. Transaction Processing in a Database Management System DBMS means handling a group of related operations as one single unit of work called a transaction. A transaction may include actions like reading data, inserting records, updating values, or deleting data. The main goal of transaction processing is to keep the database correct, consistent, and reliable, even when many users access it at the same time. A transaction follows the ACID properties. Atomicity, all operations are completed or none. Consistency, database rules are not violated. Isolation, transactions do not affect each other. Durability, once completed, changes are permanent. Example: in a bank system, transferring 5,000 rupees from account A to account B is one transaction. Step 1, 5,000 rupees is deducted from account A. Step 2, 5,000 rupees is added to account B. If step 2 fails, step 1 must also be cancelled. This avoids money loss. Easy to remember. Transaction processing is equal to safe, complete, and reliable database work. Next important short question is 2. Authorization DBMS. Authorization in a database management system DBMS means giving permission to users to access or use database resources. It decides who can do what in the database. Even if a user is valid, they can perform only the actions they are allowed to do, such as select, insert, update, or delete. Authorization helps in protecting data from misuse, errors, and unauthorized changes. Permissions are usually given by the database administrator, DBA, using commands like grant and removed using revoke. Example: in a college database, a student is allowed to view marks, select. A faculty member can update marks, update. Only the admin can add or delete student records. If a student tries to delete records, the system will deny access. Easy to remember. Authorization is equal to right user, right permission, right action. It ensures data safety and proper control in the database. Next important short question is 3. Access Control DBMS. Access control in a database management system DBMS is the method used to control who can access the database and how they can use it. It works along with authentication, who the user is, and authorization, what the user is allowed to do. Access control ensures that only permitted users can read, write, or modify data. Access control uses rules, roles, and permissions to protect important information. It helps in preventing data theft, misuse, and accidental changes. Example: in a hospital database, doctors can view and update patient records. Nurses can only view patient details. Reception staff can enter appointment data but cannot see medical reports. If an unauthorized user tries to access patient data, the system blocks them. Easy to remember. Access control is equal to control access, protect data, prevent misuse. Next, Unit 4. Long questions. First important long question is 1. Describe the concept of database security with suitable examples. Database security concept with examples. Database security refers to all the measures and techniques used to protect a database from unauthorized access, misuse, data loss, and damage. The main aim of database security is to ensure the CI principle confidentiality, integrity, and availability of data. 1. Confidentiality means only authorized users can see the data. 2. Integrity means data should be accurate and should not be changed without permission. 3. Availability means data should be available to authorized users whenever required. Database security is achieved using several methods such as authentication, authorization, access control, encryption, backups, and auditing. Key components of database security. 1. Authentication. It verifies the identity of users using usernames, passwords, OTPs, or biometric methods. Example, an employee must enter a valid login ID and password to access the company database. 2. Authorization and access control. After login, the system decides what actions a user can perform, read, insert, update, delete. Example, in a college database, students can view marks, but only faculty can update marks. 3. Encryption. Sensitive data is stored in coded form so that even if data is stolen, it cannot be understood. Example, bank account numbers are stored in encrypted form. 4. Backup and recovery. Regular backups protect data from accidental deletion, system failure, or cyber attacks. Example, if a server crashes, data can be restored from backup files. 5. Auditing and monitoring. The system keeps a record of who accessed the database and what changes were made. Example, an audit log records if an employee tries to access confidential payroll data. Real-life example. In an Indian bank database, customer details, ATM pins, and transaction records are highly sensitive. Only authorized bank officials can access them, data is encrypted, and regular backups are taken. Any suspicious activity is monitored. Easy to remember. Database security is equal to right person, right data, right time, safely. Next important long question is 2. Concurrency control, DBMS. Concurrency control in a database management system, DBMS, is a technique used to manage simultaneous operations on the database without causing inconsistencies or errors. In real-life databases, multiple users often access or update the same data at the same time. Concurrency control ensures that these operations do not interfere with each other and the database remains correct and consistent. Why concurrency control is important? When multiple transactions occur simultaneously, problems like the following may arise. 1. Lost update problem. Two users update the same data at the same time, and one user's update is overwritten. 2. Temporary inconsistency. A transaction reads incomplete data from another transaction that has not yet finished. 3. Uncommitted dependency. Data changes are used before the first transaction is finalized. Concurrency control prevents these problems and ensures ACID properties. Atomicity, all or nothing. Consistency, rules are not broken. Isolation, transactions do not affect each other. Durability, completed changes are permanent. Techniques of concurrency control. 1. Locking. A transaction locks the data it is using so others cannot modify it until the transaction finishes. Example, when a bank teller updates account A, another teller cannot change it until the update is done. 2. Timestamp ordering. Each transaction is assigned a timestamp, and the system ensures that older transactions are executed first to avoid conflicts. 3. Optimistic concurrency control. Transactions proceed without restrictions, but before committing, the system checks for conflicts. If found, the transaction is rolled back. Example: consider two employees updating the salary of an employee in a payroll system. Without concurrency control, one employee's update could overwrite the others, causing errors. With locking, one employee completes the update while the other waits, maintaining accuracy. Easy to remember. Concurrency control is equal to multiple users, one safe database. It ensures all transactions are accurate, isolated, and consistent even when many people work on the database simultaneously. Next important long question is: 3. Explain ACID properties. ACID properties in DBMS. In a database management system, DBMS, ACID properties ensure that database transactions are safe, reliable, and consistent, even when multiple users access the database simultaneously. The term ACID stands for atomicity, consistency, isolation, and durability. 1. Atomicity, all or nothing. A transaction is a set of operations that must be completed entirely or not at all. If any part fails, the entire transaction is rolled back. Example: transferring 5,000 rupees from account A to account B. 5,000 rupees deducted from A. 5,000 rupees added to B fails. The system rolls back, and A's balance is restored. 2. Consistency. Rules are maintained. A transaction must leave the database in a valid state, following all rules and constraints. Example: in a student database, total marks should never exceed the maximum allowed. Any update must maintain this rule. 3. Isolation. Transactions don't interfere. Transactions running at the same time should not affect each other. Each transaction should behave as if it is the only one in the system. Example: two bank tellers updating different accounts simultaneously will not interfere with each other's transactions. 4. Durability. Permanent changes. Once a transaction is successfully completed, its changes are permanent, even if the system crashes immediately after. Example: after transferring money, the updated balances in the bank database remain saved even if the server shuts down. Real-life example: in an online shopping system, when a user places an order, 1. Inventory is updated, atomicity and consistency. 2. Payment is processed, isolation. 3. Order confirmation is saved permanently, durability. Easy way to remember ACID. A. All or nothing, atomicity. C. Correct and consistent, consistency. I. Independent transactions, isolation. D. Data is permanent, durability. ACID is equal to safe, reliable, and accurate transactions every time. This makes transactions trustworthy, even in multi-user environments, and is a must-know topic for exams. Next important long question is: 4. Serializability of scheduling, DBMS. Serializability is a key concept in database management systems, DBMS, that ensures correct results when multiple transactions execute at the same time. When many users work on the same database, their transactions may interleave. If not managed properly, this can lead to inconsistencies. Serializability ensures that even if transactions run concurrently, the outcome is the same as if they had run one after another, serially. Why serializability is important? Multiple transactions can read and write the same data. If transactions are not properly scheduled, errors like lost updates, temporary inconsistency, or uncommitted data can occur. Serializability is a safety measure to maintain the integrity of the database while allowing concurrent execution for better performance. Types of serializability. 1. Conflict serializability. Transactions are considered equivalent if the order of conflicting operations, read-write on the same data, is the same as in some serial schedule. 2. View serializability. Transactions are equivalent if the final database state and the data read by transactions are the same as in some serial schedule. Example. Imagine a bank database. Transaction T1, transfer 2000 rupees from account A to account B. Transaction T2, deduct a 100 rupee service fee from account B. If T1 and T2 run at the same time without proper control, BS balance could be updated incorrectly. Serializability ensures that the result will be as if T1 and T2 were executed one after the other, maintaining correctness. Serial Schedule 1, T1 T2. Serial Schedule 2, T2 T1. Both schedules are correct, but the concurrent execution must result in one of these serial outcomes. Easy to remember. Serializability is equal to safe concurrency. Concurrent but correct, like lining up coins one by one. It allows multiple users to work efficiently without compromising data integrity, which is crucial for real-world systems like banking, shopping, and airline reservations. Next important long question is 5. Locking and timestamp-based schedulers, DBMS. In a database management system, DBMS, when multiple transactions run at the same time, there is a risk of conflict. To handle this and maintain data consistency, two main methods are used: locking and timestamp-based scheduling. 1. Locking technique. Locking controls access to data by allowing a transaction to lock a data item while it is being used. Other transactions must wait until the lock is released. Types of locks. 1. Shared lock. S-lock used for reading data. Multiple transactions can read the same data simultaneously. 2. Exclusive lock. X-lock used for writing or updating data. Only one transaction can hold the lock, others must wait. Example. In a banking system, T1 is transferring 1000 rupees from account A to B. T1 locks account A while updating. T2 wants to update account A. T2 must wait until T1 finishes and releases the lock. This prevents lost updates and inconsistent data. 2. Timestamp-based scheduling. This method assigns a unique timestamp to each transaction when it starts. The database uses the timestamp to decide the order of execution, ensuring that older transactions are executed before newer ones. Rules. If a transaction tries to perform an operation on a data item that violates the timestamp order, it is rolled back and restarted. This method avoids deadlocks, where two transactions wait indefinitely for each other. Example. T1 starts at 10 a.m., T2 starts at 10:05 a.m. T1 wants to read account A, T2 wants to update account A. Since T1 is older, it executes first. T2 may wait or restart to maintain correct order. Key points to remember. Locking ensures safety but may cause deadlocks. Timestamp scheduling avoids deadlocks but may restart transactions often. Both ensure serializability, meaning the database behaves as if transactions ran one after another. Easy way to remember. Locking is equal to wait your turn, timestamp is equal to follow your birth time. These techniques make the database safe, consistent, and reliable even with many users working at the same time. Next important long question is 6. Multiversion and Optimistic Concurrency Control (DBMS). In a database management system, DBMS, multiple users often access and modify data at the same time. To ensure data consistency and avoid conflicts, advanced concurrency control techniques like multiversion concurrency control (MVCC) and optimistic concurrency control (OCC) are used. 1. Multiversion concurrency control (MVCC). MVCC allows multiple versions of a data item to exist simultaneously. Each transaction works on a snapshot of the database rather than the live data. How it works? When a transaction reads data, it sees the version at the time it started. Writers create a new version instead of overwriting the existing one. Example: in an online shopping system, two users try to view and update the stock of a mobile phone. User A reads the stock as 10. User B buys one phone, a new version of the stock, 9, is created. User A can still see 10 until they commit their transaction, avoiding conflicts. Benefits: no read locks are needed. Readers never block writers, improving performance. 2. Optimistic Concurrency Control (OCC). OCC assumes that conflicts are rare, so transactions proceed without locking data. Conflicts are checked only at commit time. Phases: 1. Read phase. Transaction reads data without locks. 2. Validation phase. System checks if the data read has been changed by another transaction. 3. Write phase. If no conflict, changes are applied. Otherwise, the transaction is rolled back. Example: two employees update the same salary record. Both read the current salary of 50,000 rupees. Employee A updates it to 55,000 rupees and commits. Employee B tries to commit 52,000 rupees, but the system detects a conflict and rolls back B's transaction. Benefits: improves concurrency in low-conflict environments. Avoids deadlocks. Easy way to remember: MVCC is equal to multiple versions, everyone sees their own snapshot. OCC is equal to optimistic trust, then check at the end. These methods ensure database consistency, efficiency, and high performance even when many users work on the system simultaneously. Next important long question is 7. Explain database recovery authentication in detail. Database recovery and authentication (DBMS). In a database management system, DBMS, data is valuable. Sometimes, due to system crashes, power failures, or user errors, the database may become inconsistent or some data may be lost. To handle this, DBMS uses database recovery and ensures authentication for secure access. 1. Database recovery. Database recovery is the process of restoring the database to a correct state after a failure. Its goal is to protect data and maintain consistency. Types of failures. 1. Transaction failure. A transaction cannot complete due to an error. 2. System crash, power outage or server failure. 3. Media failure, disk or storage device damage. Recovery techniques. Rollback, undo changes of incomplete transactions. Checkpointing, periodically save database state to reduce recovery time. Redo and undo logs, maintain logs of operations to redo committed transactions and undo uncommitted ones. Example: if a bank system crashes while transferring money, transaction from account A to B is incomplete. Recovery process rolls back the operation to maintain original balances. 2. Database authentication. Authentication ensures only authorized users can access the database. User ID and password, basic check to verify identity. Biometric or two-factor authentication, advanced methods for sensitive databases. Example: a company HR database allows only HR managers to update employee salaries. Login credentials prevent unauthorized employees from accessing or changing data. 3. Importance. Recovery prevents data loss and maintains integrity. Authentication ensures security and privacy, especially for confidential data. Both together make the database reliable, safe, and trustworthy. One ensures data correctness after failure, and the other ensures secure access, keeping the database accurate and safe even in multi-user environments.